Welcome to topology class. Today we will discuss about closure operators. Last class we have discussed about closure. So definition closure of a set. You know that closure of a set A, we are having a topology xt and a subset of x, and we will say that, or we will define a closure as the intersection of all closed sets which contain A, such that Ci is closed and next condition is A is contained in Ci for every I belongs to I. So this is the condition. So we will say that this intersection is the closure. Now we are defining closure operator. First of all, what's an operator? Operator means, first we can note that an operator is another name for a function. Okay, then now this generally refers to this function is connecting from sets of sets whose domain is sets of sets. So an operator is just another name is just another name for a function, for a function, except that except that the term is generally the term is generally reserved for the function whose domains are sets of sets or functions whose domain are sets of sets or functions. In that case, we will say that uh, this function is an operator. That is, suppose you are having a function from this x to y, you are having a function f. Now suppose this itself contains so many sets. Okay, suppose this, now here you are having c, this is connecting to d, this is connecting to f, something like the map is there, means this map we will call it as an operator. Okay, so the codomain, sorry, the domain should be either sets or functions. In that case, we will say that this function is an operator. Next definition, 1.5 definition. 1.5 closure operator. Closure operator. If xt is a topological space, then the closure operator associated with it is associated with it is defined as the function c from p of x to p of x, power set of x to power set of x. See, we are taking power set, so it is collection of sets. So this is an operator, c from p of x to p of x, such that closure of a or c of a equal to a closure for each a belongs to p of x. It means we are mapping from here. We are having collection of subsets. A, here is we are having a, b. Suppose here we are having c. Now we are mapping this to p of x to p of x. So it is a, b, c. This empty set. This is b, c. Suppose I have got like this. Now from x to x I am mapping from p of x to p of x. So suppose I am mapping like this. Any map. We will say that suppose this is the closure of this, then we will say that this is a closure operator. Thus, first condition, empty set is fixed point, is a fixed point of C, of this operator. Meaning is that when you are finding C of empty set, you will get the empty set. It's clear? Because you are finding the closure. Closure of empty set is empty set. And secondly, the fixed points of C are precisely the closed subsets of X. From where you got this? This means we know that we have studied last class A is closed if and only if A closure is equal to A, right? Now fixed point means C of A we are defining as A closure. So fixed point means C of A should be equal to A. That is possible only if A is closed. So fixed points are precisely the closed subset of X. The third one, C is idempotent. C is ID or EM potent, P-O-T-E-N-T, idempotent. That is, the meaning is that C composition C is equal to C. Or in other words, what you're having is for any A belongs to P of X, C of A is equal to C of A. C of A is equal to C of A. That means since we have studied that A closure is equal to A closure, right? So it follows immediately. In the fourth one, C commutes with finite union. C commutes with finite union. This also we have proved, since A union B closure is equal to A closure union B closure. You have proved this last class. Okay, so C commutes with finite union. So this proof we have already proved. So I'm going to next theorem, 1.5 theorem. X be a set X be a set and theta from P of X to P of X theta from P of X to P of X, a function such that first one, for every A belongs to P of X, A belongs to P of X, A is contained in theta of A. A belongs to P of X, then A is contained in theta of A. We will say that theta is an expansive operator. Is an expansive operator. Meaning is A is contained in theta of A. Second one, empty set is a fixed point of theta. And third one, theta is idempotent. Theta is idempotent. Fourth one, theta commutes with finite union. Finite union. So these are the conditions. So first one, for every A belongs to P of X, A is contained in theta of A. That is, theta is an expansive operator. Second one, empty set is a fixed point of theta and theta is idempotent. And the last one, theta commutes with finite union. So this exactly resembles what you written previously, right? This one, same closure operator. So what we are going to do is, we will prove that then there exists a topology such that this theta coincides with its closure operator, and converse part is also true. Then there exists a unique topology tau or T on X such that this theta coincides with the closure operator associated with T. And conversely, any closure operator satisfies these properties. these properties. So any closure operators will satisfy this property. That's evident. So what we want to prove is there exists a unique topology T on X such that this theta is coincides with the closure operator associated with T. Proof. Suppose theta from P of X to P of X satisfies the above four condition. Satisfies the above four conditions. We want to find a topology. We want to find a topology T. I'm representing it as some Tt, okay, on X such that for every A belongs to X, for every A contained in X, my theta of A is equal to A closure. So what we want to prove? So we are supposing that we have got an operator theta satisfy the four conditions. Now we want to define a topology on X such that for every A subset of A, this theta operator coincides with a closure operator. Now, what's the specialty? Now, if such a thing is existing, if at all such a topology exists, then its closed subsets must be precisely the fixed point of the fixed points of theta. So inside the bracket. Now let some collection we are taking C equal to set of all A subset of A such that theta of A is equal to A. So what is the specialty of this? See, this means exactly it should be the closed sets. Then we can go for its complement, that is open sets. That means once you define the open set, we know what is the topology. So our aim is like that. So we're taking the collection C, which is equal to set of all A subset of X such that theta of A is equal to A. And we agree that, and we or we claim that we claim that C has properties. C has properties 1 to 3 of the theorem. 1 to 3 of theorem 1.2. Okay, theorem 1.2 we have discussed in the previous class. What was that? That is, the empty set and X belongs to C, and C is closed under arbitrary indecision, and C is closed under finite union. That is topology conditions, right? Now condition 2, conditions 2 shows that empty set is a fixed point, we have said. So this belongs to our collection C, while condition 4 implies C is closed under finite union. Now to prove X belongs to C. Now to prove X belongs to C. From 1, X is contained in theta of X, right? And hence, and theta of X means at theta of X is a contained in power set of X, and X is contained in theta of X. This should be satisfied, which implies your X is nothing but theta of X. Okay, therefore, or since no need of writing, we have already mentioned it here. Okay, so theta of X is contained in P of X. That means theta of X is a subset of X which is containing X. That means theta of X should be nothing but our X itself. Now it only remains to it only remains to verify that C is closed under arbitrary indecision. C is closed under arbitrary intersections. C is closed under arbitrary intersections. For that, what we want to do? For this, we must note that for this, we first note that theta is monotonic. Theta is monotonic. That is, whenever A subset of B and theta of A subset of theta of B This is the meaning of monotony. That is, if A is contained in B, then theta of A is contained in theta of B. So this is called the monotony. Proof. Let A subset of B and B equal to A union B minus A. Suppose we are finding like that. Now by property 4, by fourth property, theta commutes with finite unions. Therefore, what you're getting is theta of B is equal to theta of A union theta of B minus A, right? Which implies theta of A is contained in theta of B, am I right? So what you got is A is contained in B means theta of A is contained in theta of B. Okay, that is theta is monotonic. That is theta is monotonic. We have proved our theta is monotonic. Now let let A equal to intersection I belongs to I of AI, where I is an indexed set and indexed set and our AI belongs to C. For each I belongs to I. Now we want to show that A belongs to C, that is theta of A equal to A. Now we will say that A equal to intersection of AI. Okay, indexed set where I is an indexed set and AI belongs to our collection. Now for each I, we want to show that A belongs to C. Then it is a closed under finite intersection, right? That is theta of A is equal to A that we want to prove. So by theorem 1.2, the family T of complements of members of complements of members of C is a topology on X. Now it remains to verify that the closure operator associated with this tau coincides with theta. Now it remains to be verified that the closure operator associated with this tau coincides with theta. That we will do in our next class. So today what we have done is, first of all, we have defined what is a closure operator, an operator, then a closure operator, then a property of closure, then that property we are having a theorem here. But the theorem says if theta is an expansive operator, then that theta it will satisfy some four conditions. That is, first condition is theta is expansive, then fixed point of theta is empty set, theta is idempotent, and theta commutes with finite union. Then this theta coincides with the closed subset or the closure operator of a unique topology on that set. And today we have seen that with this theta operator, we are define a set C is that A contained in a subset of X such that theta of A is equal to A. And we will claim that C has the property of theorem 1.2, that is theorem 1.2 says that this C is what does this mean is this theorem actually says phi or empty set and X belongs to this collection and C is closed under arbitrary intersection and finite union. So we will claim that now this C will satisfy these three conditions. Then at first we have seen that empty set belongs to C because given that empty set is a fixed point. Now we have shown that X is also belongs to C. See, X is equal to theta of X. That implies your X belongs to C. Next we will show that it is closed under arbitrary intersections. Now for that, first we will prove that theta is monotonic. Monotonic means if A is contained in B and theta of A is contained in theta of B. This condition is called monotonic. So we have proved the monotonicity. Then we'll take the arbitrary intersection. And in that intersection, we have shown that it will satisfy the arbitrary intersection. Now whatever is remaining for us is that to verify that the closure associated with a topology is coinciding with our C. Okay, so hope you understood today's class. Thank you for your patient listening. Thank you.